Okay, well, so welcome to lesson 17. Excuse me. Hate to start with a throat clearing, but all right. So today we're going to work three examples. We're going to apply the energy equation in combination with continuity, momentum, hydrostatics, etc. So in other words, here's the energy equation right here. Perhaps one of the most useful equations in all of fluid mechanics. And let's see. So just as kind of a reminder, we've got the pressure terms at two locations. These are actually ins and outs. Because this works on a control volume. Here are the elevations of the in and the out. And here's the velocity head, in and out. Noticing that the velocity head in this case is a bar to represent the fact that it is average. And it has this little alpha, which is a correction factor, which normally we can ignore. We can just make it 1 and kind of forget about it. Oftentimes it'll need to be 2, or sometimes it'll need to be 2 if you have laminar flow. Pretty rare. And then we've got head due to pump, turbines, and then energy lost due to losses. So usually just kind of friction, viscosity, et cetera, et cetera. So, and of course, we're going to, as we go through the rest of the semester, we're going to be talking about how to nail down exactly what that head loss is. Some problems will be easier than others, okay? So we're going to do that in combination with our tools. So I'm going to bring our tools over here so that we have them ready to go. Okay, so we'll go down here. Here's example 1. And basically we've got a pipe and it's got water in it, and it's got 2 points A and B. And so in some ways this kind of defines a control volume for us, so I'm going to go ahead and define our control volume as being the entire pipe. Notice that there is pressure at both A and B, which can be seen in 2 ways. One, the way I've drawn this with the kind of little opening there, which says that the pipe just continues on indefinitely. But the other way is that we've got pressures that are given to us, 29.4 psi at A and 25 psi at B. Notice that as the water, the difference in elevation from A to B is 12 inches, but the difference in pressure, it looks like it's about 4.4 psi. So one of the questions here, and I used to like to ask this in person, is which way is the water flowing? Does anybody have any ideas which way the water is flowing? And usually what happens is I'll get a few different answers for this, and it's helpful for you to think about this. But there's a reason to think that the water would flow this way. And that reason is that the pressure at A is higher than the pressure at B. So that would tend to drive the flow uphill. However, and that's because PA is greater than PB. However, we might also think that the water is going to go that way. And the reason for that is because ZA is less than ZB. So really kind of the question here is the difference in pressure enough to drive the water uphill? Okay, or does the water in fact follow gravity? Okay, so that's kind of our question. And so what we're going to do here is we're going to determine the head loss and the direction. And the purpose of this problem is to make note of one important thing. Notice the head loss is always on the outside of the equation. Okay, it is not on the inside of the equation. Like I could have put it on the left, which would be where all the things that are giving energy to the system, I could have put it over there, but it didn't. Well, I say I could have. We couldn't have. And the reason for that is because it has to be positive. It represents a loss. It is a loss and is represented positive. Okay, so looks like I'm going to have to leave that there. I think I have a spare. I do have a spare. Okay, let's bring this down here. Okay, how do I know, for example, here, in this case, that I'm going to need this equation, right? We've got a bunch of tools. How did I know right off the bat that I needed an energy equation? Well, there was a huge key was right here. I'm looking for head loss. None of these other equations have head loss. And that's kind of the number 1 key. It looks like clearly we're going to need to know the geometry of this problem, right? Because, we need Z1 and Z2. Continuity is going to come into play. There is no manometer, so we're not going to need a manometer. And we're not going to need momentum. And the reason we know we're not going to need momentum is because you always need the momentum problem when they ask about forces in moving fluids. And this has nothing to do with forces on a moving fluid. Okay, so let's go ahead and start getting to work on this. And one of the things that, a big, bugaboo here is this alpha. But the nice thing here is that if I do continuity off to the side, let's do continuity off to the side real quick. Let's just get rid of that, okay? Or you know what, let's go term by term. We'll get to the alpha in a second. Let's go term by term. Let's start with the pressures. Well, we know the pressures, right? But the pressures are annoying because they gave it to us in PSI. We hate PSI. Why do we hate PSI? Because it's a non-standard unit, right? So we want pounds per square inch. Let's go ahead and convert that. I'm going to go ahead and convert it on the diagram because this is not so complicated that we need to like do a whole lot with it. So what we do is we basically multiply by 144. So that's the number of square inches in a square foot. Okay, so we get these numbers. All right, so now we can go down here to our pressures. Come on, man. Really? No, you can do it. There you go. It's really very complicated, isn't it? All right, so P1. So we've got this term, we've got this term. Okay, we just need to plug those numbers in. Zeta 1 and zeta 2, well, we're going to make Z1 right here, or ZA in this case. You can kind of turn those into A's and B's. Okay, so zeta A and zeta B, well, we're going to turn to our geometry in this case. I'm going to notice that whatever A is, B is 1 foot higher. So zeta A is going to be 0, and zeta B will be 1 foot. Okay, now we got to do VA right here, and VB right here. And we need to figure out what those are. Now, the nice thing is, from continuity, the area of the pipe at B and the area of the pipe at A are the same. So VA equals VB by continuity. So it doesn't matter what this is because it's the same thing as it is here. So those two by algebra go away. We don't have a pump. We don't have a turbine, but we do have head loss. Oh, it looks like, and I didn't even think about this, but I assumed the water was going this way, okay, without knowing the direction. How do I know I assumed that? Because I put A over here at the in and B over here at the out, okay? So let's go ahead and start working this problem. So PA is 4233.6 PSF over 62.4 PCF. Okay, we don't have this term goes away. This term goes away by algebra. There's no pump. So that equals PB, which is 3600 PSF over 62.4 PCF, plus a foot, plus the head loss. Okay? So what I'm going to do is I'm going to kind of combine these two terms by bringing the 3600 over 62.4 over to the right. And so we're going to end up with equals, I know I'm putting in an extra step and no one likes that, but I'm the teacher and there are reasons for it. So, and look at that. It looks like the pressure head, the difference in the pressure heads was 10.2 feet and the difference in the elevation was 1 foot. So basically, it looks like the head loss in this case turns out to be a positive 9.154 feet, or the head loss equals 9.15 feet. Okay, now because that is a positive sign, that means we chose the correct direction here. That means that the flow is in fact from A to B. If we got a negative sign, so for example, if this 1 foot, if I tried to drive this flow up, let's say 12 feet, then I wouldn't have had enough to do it. Like I would have gotten a negative head loss. In that case, I would have gotten a negative 1.85 feet, and it would not have been able to move the flow that far. And so we would have had to say, okay, well, it obviously is going to go the other way. So what's cool about this, and by setting it up this way, as I set it up right here, is this is how high that pressure difference can pump the water, okay? 10.154 feet. Any more than that, and it's not going to move the water. Any less, and it's not going to make it, okay? So the nice thing about this is this also tells us the head loss. Now, note, if you'd solved this, like let's imagine in an alternate universe where instead of giving you 1 foot for this elevation change, let's suppose I'd given you 100 feet. 100 feet. Okay, well, you'd be like, okay, well, now we're going to solve that. And instead of getting 9.54, we would get 89.85 feet negative. Okay, and you'd be like, oh my God, so that's negative 89.9 feet. Well, then what would happen? Well, then you would say, well, the flow is actually from B to A, and the head loss from B to A is the opposite sign, is negative 89.9 feet. okay, which is pretty crazy, right? So basically, this is how high up you can go. You can with a pump differential, a pressure differential of how many psi was that? 4.4 psi. You're going to be able to cause water to go up 10.15 feet, okay, and no more. If you try to go up 100, you ain't going to make it, okay? It's going to come backwards on you, okay, or just with the pressure. All right, so that said, let's do another example. It looks like I've got a spare energy equation, since it seems like we're probably going to need it. So let's go ahead and put that over there. I think I don't have spare tools. I'll have to make some more spare tools. But let's create the problem. All right. Okay, so here we have a siphon. And so what a siphon is, and this is kind of an interesting thing. Some of you may have tried to, in your more troubled youth days, tried to siphon off someone's gas as a way to steal it. It's pretty rude of you. But basically, we've got a tank full of, I don't really know what this is a tank full of. It looks like it must be water. Okay, so this is a little bit nicer. So basically, or you could, if you prefer, I used to do this a lot with my fish tanks, as a way to empty the fish tank. What you do is you put a tube, so this tube would be called the siphon. And what you do is so the tube, in this case, the tube is 8 inches in diameter, which of course, that would be very hard to use as a siphon, because I usually like to siphon my fish tank by starting it with my mouth. And basically what you do is you start sucking basically at C, and you pull the water from the reservoir at A, and you pull it up until it gets to B. And once it gets to B, it starts to fall down to C, and then the water just keeps flowing, which is pretty freaking cool, right? And so you can basically drain the whole fish tank without doing much work, except for that initial suck, which of course, if your fish tank hasn't been cleaned in a while, it can be a little disgusting. So anyway, so if you're into fish, it's very cool. If you want to go steal some gas, this is how you do it. Please don't go steal anybody's gas. Sucking gas in your mouth is probably very unhealthy. All right, so anyway, in this case, we're siphoning water from this tank, and what's happening is it's flowing through this 8-inch pipe all the way to B and then out through C. Okay, and it's flowing at a flow rate, Q, of 2.8 cubic feet per second. Remember, that's what the CFS stands for. And again, we've got some tools here that are going for us. We've got energy, geometry, continuity, manometer, momentum. Okay, so we want to determine the head loss through the system. So right there, when you see head loss through the system, we're thinking energy. Okay, so that's going to be our master, right? And of course, for some reason, my energy equation has attached to everything else in here, and I can't move it, which is totally annoying. All right, got it. Okay, so maybe if it'll let me, it's not going to let me resize it. All right, anyway, so what we're going to do here, if that is our master, is I'm going to start thinking about these terms and think about what I want to do. So it wants the head loss through the system. So if it wants head loss through the system, that means it wants the head loss, maybe we'll start at A, and I'll go all the way to C. So that means my control volume is kind of the whole thing. Okay, so it's kind of what's flowing in at A, and it's flowing, kind of like this, I guess, all along that wall, and then like that, okay, and then control volume ends there. So basically it's all the fluid in this sucker. And so A is kind of like in right here, okay, and out is at C right here. Okay, so what I'm going to do, let's zoom in and let's look at it, and we'll consider our tools as we kind of attack this one at a time. And the first thing that I need to do, because I didn't really talk about this very much, is I just went straight to A and decided that A was going to be my entry, my beginning point. Now, a mistake that a lot of my students will make is that they will decide they want to start at B. Now, the problem with starting at B is simple. Well, there's a few problems with it, but the most prominent of which is that right now, for this first part, we're trying to determine the head loss through the whole system. So to determine that, I need to go from the beginning of the system till the end of the system. Okay, so it's kind of got to be at A. The other problem is I don't know anything about the pressure at B. There's a temptation to say, well, I know the pressure at C because it's atmospheric, because it's exiting the pipe, and so then I can just work backwards up the pipe until I get to B. You actually can do that, but there's a problem here, which is that this is not hydrostatic. Okay, so this manometer equation or your hydrostatics equations aren't going to work here because the fluid is moving. Okay, so we can't use hydrostatics. Okay, you can, I mean, technically there is a region in the tank where you can use it, and it's probably some distance sufficiently far from this entrance. Okay, like if you're out here, you can probably pretty well assume that the fluid is basically not moving. But basically what the fluid's doing everywhere is it's getting pulled towards that opening, and as it approaches that opening, it's going to accelerate, right? And so once it gets going fast enough, you can no longer assume that it's not moving. So I wouldn't even know exactly how to define what that distance is to that opening before we would no longer be able to assume hydrostatics. So I don't really want to do that. So instead what we're going to do is we're going to go at A, and others of my students will like to put like an alternate A, maybe I'll call that A prime, like right here. Okay, and again, the problem there is what's the pressure? The fluid is moving. Where exactly is that depth-wise? You know, so I mean, there's just a lot of problems kind of defining that. But if I choose A, so if I make all of these 1s into A's, then what that does for me is it means that, well, the pressure at A becomes 0. Why? Because this is gauge pressure, right? So that's atmospheric. The zeta at A, well, I mean, the Z at A, well, let's see. Maybe if we're going from A to C, we'll make this our datum. So C will be 0, which means A will be 3 feet. So we're kind of picking a point where we know stuff. And then the velocity at A, oh, well, that's 0 because of the tank assumption, right? The tank or the Tahoe assumption or whatever you want to call it. Okay, we don't have a pump. So that whole left-hand side of the equation becomes relatively easy. It becomes 3 feet. Okay? Now the pressure 2, which now becomes C. So we're going to make this because we're going all the way through the whole system. Okay, the pressure at C, well, that's atmospheric, so we're going to go 0 gauge. Okay, the Z at C, well, that's, what's Z at C? It looks like that's the datum, so that's 0 because of the datum. Okay, and then the velocity at C, well, how do we get at that? Let's come back to that in a second. There's no turbine, and there's a head loss. The head loss is what we want to look for, so this is going to be plus the head loss. Okay, so how do we get V at C? Okay, so we know this is going to be alpha. We know this is going to be 2 times, let's see, G, we're in feet, so we need 32.2 feet per second squared. Okay, so now I need VC. Okay, so we go back up to our tools, and usually if we want to get velocities, we go to continuity. That makes sense in this case because we have Q. Okay, so we'll go over here and we'll say Q equals VA. Oh, hey, pup. Hey, oh, you want me to throw this ball for you? Okay, give me 1 second. I have to throw a ball. So at this point, we've seen, this continuity done really, quite a few times. So this should be becoming old hat. So I guess we could put C's on here if we wanted to. So VC, and we'll call this area, which would be pi times 8 inches, 8 over 12 feet squared over 4. So VC equals, I think 8.02 feet per second. Okay. So I don't really like the fact that I kind of got a little bit into my own business, but here we go, 8.02 feet per second. And the puppy is going and breaking things behind me. And so what we're going to do here, and now you're kind of saying to yourself, well, what are we going to do about this alpha? And what I recommend is if you're like low on time, you just assume it's 1 and you move on. If you have time, go ahead and check it. Okay, so basically what we're going to do is we're going to check to see if this flow is turbulent. So what we'll do to do that is we're going to check the Reynolds number. Okay, so the Reynolds number is VD or nu. Okay, so it's going to be 8. Well, let's give ourselves a little bit of room. 8.02 feet per second. Okay, times the diameter, which is 8 over 12 feet. Okay, over nu. Okay, and the kinematic viscosity of water is roughly 1.4 times 10 to the negative 5th feet squared per second. That's at 50 degrees C. Again, I've kind of mentioned this before. I wouldn't really worry too much about the 10 to the minus, this number right here. You could have just put in 1, and it's going to give you the basic idea. I really wouldn't even worry about this number right here all that much unless it's like really huge or really small, because all we're trying to do is get an order of magnitude estimate here. And basically, kind of if I stare at this without even pulling out my calculator, it's going to be about 8 times 10 to the 5th, okay, order of magnitude, or basically order of magnitude, it's 1 times 10 to the 6th. Okay, now you're saying, wait a second, I'm going to plug that into my calculator. I don't think that's right. And of course, you'd be right. Like if you actually plug this into your calculator, you'd actually get something more like 3.8 times 10 to the 5th. Okay, but notice it doesn't really matter. Okay, because what we're comparing this to is about somewhere in the range of 2,000 to 4,000. And if the number is greater than 4,000, and it turns out we are 2 or 3 orders of magnitude above that, then this is turbulent and alpha equals 1. So there's no reason to really get all stressed out about this. Okay, so whether you plug this into your calculator and get this, or whether you just kind of estimate and get this, what I recommend is kind of like you just do this in your head to see if it's even close. It's usually not even going to be close. So if I do this in my head and I just said 8 divided by 10 to the minus 5, well, that's 8 times 10 to the 5th, okay? So that's pretty quick and dirty, and you know that that is much larger than this 4,000, okay? So alpha equals 1 because it's turbulent, because it's greater than that number right there, okay? So what we're going to do is we're going to go back to our problem, the thing that we're working on over here, and alpha equals 1, and so we plug this in, and we end up with 3 feet equals what boils out to a nice, pretty, basically 1 foot plus the head loss, okay? So the head loss is 2 feet. So the way I think about this, always, okay, A is 3 feet above B, excuse me, above C. So that's what's driving it through the column, okay, from A to C. And some of that energy is used up to create the velocity, and the rest of it is lost to head. Okay, so 2 feet is lost to head, 1 foot becomes velocity, and altogether that's the 3 feet that you put in. Okay, so that's the first part, that's A. Now B, what is the pressure at B? And so to get the pressure at B, what we need, well, we need another energy equation. Let's see if I can get another energy equation. So I'm going to take this one right here, if I can grab it. It doesn't look like it wants me to do that. I'm going to do this off screen. Okay, so I was able to duplicate it, and if we come back over here, here it is. And what I'm going to do here, actually, I'm going to duplicate this twice because I want to demonstrate something that I feel like kind of gets lost on my students sometimes. And so what I'm going to do is I'm going to duplicate it, and I'm going to take this duplicate, and I'm going to put it, I don't know, where, somewhere else. I'm going to put it over here. Okay, and we'll deal with that in a second. So first what I want to do is I'm going to go and I'm going to solve this same problem. So determine PB equals what if 2/3 of the head loss, so 2/3 of 2 feet is what, 4/3. So 4/3 of the head loss, or 4/3 of a foot of head loss, occurs between the reservoir and A, okay, and B. So that means from A to B, so this is going to be A and this is going to be B. Okay, so let's go ahead and let's look at that and let's think about what this means. So one nice thing about this is we've already done the A side of this equation. Look, it's the same as it was right here. Nothing has changed. There's still not a pump between A and B. You know, the A is still at the surface, and ZA is still at 3 feet, and the tank is still the tank. So basically, this is 3 feet equals. Now this side, this 2 becomes a B, this becomes a B, this becomes a B. Okay? So we can go ahead and start thinking about this. What we're looking for right now is the pressure at B, okay, divided by gamma, which is 62.4 PCF. The Z at B, okay, well, let's see what that is. Looks like if you look at the diagram, it's 3 feet above the water surface, so it's going to be 3 feet. Okay? Alpha VB squared on 2G. Now there's an issue here, which is, what is the velocity at B? Well, notice that this pipe has a constant diameter of 8 inches. So it's the exact same thing as it was up here. So up here, alpha V squared on 2G right here was 1 foot. So I'm going to put in 1 foot right there. There's no turbine. Okay, plus 4/3 of a foot. Okay, so this is a little bit interesting, right? So I think, hopefully you're seeing some weird things here, okay? Because I'm seeing some weird things, right? What are you seeing here? Hopefully you're seeing some things. Okay, the first thing you should be seeing is that I made a mistake, and that this number right here, ZB, is 6 feet. Did you catch that? Okay, let's go back up here. Oh, come on. That's really annoying. Roughly right there. Okay, so if we go back up to our drawing, okay, notice that I decided, and you can move the datum around as long as each time you use the energy equation, you hold the datum steady through that whole portion. But I decided to make A the same as it was before. So if I did that, then the datum has to stay where it was. So the datum is down here. So that means A is at 3 feet, B is at 6 feet. Okay, so that's an important error. The other thing to note here, if I can zoom in, is, you've probably noticed I like to think about what's going on here. So I've got 3 feet of elevation here. And with that 3 feet, here's what I'm doing. I'm going to raise the water another 3 feet. I'm going to create a foot of velocity head, and I'm going to lose 4/3 of a foot due to energy. This sounds energetically impossible, right? Because I'm only putting in 3 feet of energy, and I'm getting out a whole heck of a lot more. So how is that possible? Okay, and here's how it's possible. If I solve for PB, what am I going to get? I'm going to get a negative number, right? And in this case, it's negative 332.7 feet. Excuse me, 8. And that's PSF. Okay, so that's a real number, right? And it's negative. So basically, I started with a 0 pressure, and all of this energy came basically by losing energy at the pressure. So basically, in a scale, basically I was able to lose pressure, and that pressure went into creating a velocity, right? And I still was able to lose energy. Okay. Now, remember, this is a gauge pressure, so it can go negative. However, when we get negative pressures, what this means is that it's 332.8 PSF below atmospheric. Okay? It doesn't mean that it's below absolute 0. It means it's below, 0 for the atmosphere. So the next question that will commonly be asked, if you see a negative pressure, okay, and I like to throw these problems on the test because they trip up students, but it's something to remember. This is totally possible. Okay, and the next question that shows up all the time is, will it cavitate? Okay, meaning, is this pressure low enough for the fluid to essentially vaporize, just kind of like in the pipe, okay? And, well, let's think about that. So what we need to do is we need to look up the vapor pressure of fluid in PSF or PSI or whatever, and here's the problem. This thing is gauge. Okay, when we look it up on a chart, it's going to come out absolute. So the pressure of vapor, okay, and let's assume we're at 50 degrees F. Okay, if I look it up, it's going to come out and it's going to be absolute. So we need to compare these two. So looking it up at 50 degrees, it looks like it gives us to us in, here we go, PSF. Okay, PSF. And I'm seeing 25.651, 25.651. Okay, so then the question is that vapor pressure greater or less than this one? Okay, and to which I answer, well, I don't know. Okay, why? Because one is absolute and one's gauge. So we need to compare these two to see if it will cavitate. Okay, and so the way we need to do this is I need to convert this absolute into a gauge. Okay, and so what I remember is that pressure absolute, okay, equals the pressure of the atmosphere plus pressure gauge. Okay, so in other words, right now I know that I'm 332.8 PSF below the atmospheric pressure. The atmospheric pressure is 14.7 psi. Okay, but of course we can't work in psi, so that's pounds per square inch. I want it in square feet, so that's going to be 144 inches squared over 1 foot squared. Okay, equals whatever this absolute pressure is going to be at B. Okay, so let's go ahead and compare that. So P absolute equals 1784 PSF. This is absolute. Okay, so That's the pressure at point B. Okay, so in the siphon. Okay, there we are. Now, so we're staring at that, and basically it was going to have to get down to 25.6 before it was going to vaporize. Okay, so it will not cavitate. Okay, so that's a good thing. The only thing though that if it will not cavitate, and usually the pressures have to get pretty low or the temperatures need to get pretty high for it to cavitate. Obviously, if the temperature gets up to 212, this is going to cavitate, you know, almost under almost any atmospheric condition. So the temperature of the water. But one thing to be aware of, if we have 1784 PSFA inside the pipe as it kind of turns over, so this is at point B. Okay, what's the pressure outside? Well, the pressure outside is this number right here, which unfortunately I didn't save in my calculator, but luckily it's not very hard to get at. So we'll say 14.7 times 144. It's 2116.8 PSFA. Okay, so note there is a pressure gradient from basically trying to crush your pipe. Okay, so if you use a siphon, and this is like flimsy, kind of like a rubber or something, you might have a case where the pipe itself will like implode or try to implode. So it's just something to consider. Okay. Anyway, that's 30 minutes, so we'll save this. But at this point, we have answered this question. You know, I went on a bit of an aside there at the end. Okay. But notice that the lowest pressure in this whole system, basically, as you move up this thing, what's happening is as you move up, due to hydrostatics, you're moving upwards in the fluid. Okay, the velocity is staying the same. Okay, but you're losing. But you're gaining elevation, so that you have to lose pressure. So this is the lowest pressure right here in the system. Okay, so this is the most likely spot for cavitation. Okay, and that's because basically all through this pipe, V is constant. Okay, because it has the same area everywhere. Okay, Z increases going this way, right? And then it decreases going that way, which means pressure is going to decrease. Okay, going from A, or from A prime, I guess, to B. Okay, obviously that will switch when we start going downhill. Okay, the Z will decrease and the pressure will increase. Okay, and obviously as you get well, maybe not obviously, but as you approach this, the pressure is going to go back to zero. Okay, so it'd actually be kind of interesting to plot the pressure going from here down to here and then all the way down back to here. Okay, so that's it, and I'll start section 2 in a second. All right, bye. As an engineer, is that